In this video, we'll review the geometric algorithm for linear programming. In 1947, George Dantzig developed the simplex method. This is an algebraic procedure which fundamental concepts are geometric. We have seen already the graphic solution. Now we're going to explain the same case through a geometric algorithm, and then we're going to work with the algebraic algorithm, and we're going to end with a tabular algorithm. Before we go further with the geometric algorithm, let's recall some terminology. We got restriction boundaries are the lines that mark the limits. We got also corner points solutions, CPF, these points of intersection between boundaries. We also have edge. When we have two CPF, the line that connect both CPFs are called edge. We also have what we call the optimality test. And if a CPF solution has no better adjacent CPF solution, then it must be an optimal solution. In this case, our optimal solution was 0.2,6. Now, this optimal test is used by simplex method for determining when an optimal solution has been reached. Now let's go over our geometric algorithm. Our performance measure is given by z equal 3x1 plus 5x2. That's our objective function. The algorithm has three mainly steps. Step number 1, where we choose the edge that enhances the performance measure. Step number 2, we stop at the next restriction boundary. And step number 3, we solve our performance measure for the intersection of the new boundaries. And then after these three steps, we do the optimality test, where we're going to be asking if there's a better adjacent solution. Now we start with our initialization, and for initialization purpose, we choose OO CPF, okay? And we pass directly, we go to the optimality test, where we ask if there's a better adjacent CPF. The performance measure with OO gives us 0. And then we have the adjacents, where here, OO, our adjacent CPFs are 06 and 40. So my performance measure with 06 gives me 30, and my performance measure with 40 gives me 12. So do we have a better performance against this one? Yes, we do, with 06. So that means we go to our next CPF. Now we go to iteration number 1, and we're going to follow the algorithm. It says we choose the edge that enhances the performance measure. Remember that the performance measure is given by 3x1 plus 5x2. So if I measure how many is going to be enhancing this performance, if I choose 3x1, I will be enhancing 3 units, but if I choose 5x2, I will be enhancing 5 units. So I'll be choosing x2 because it has a better enhance. That means from this point, we're gonna move through the edge that goes to 06. And this edge, we're not going to consider it. Okay, so step number 2. At the next, we stop at the next restriction boundaries. So we decide to go all this way, and here we got one restriction boundaries that was it was x2 equals 6. Okay, so we stop there, and we see that at this point we got this 06 value. So we solve the performance measure for the intersection of the new boundaries. That means we're going to be measuring with 06, and it gives us 30. Now we go to the optimality test, and here we're going to ask again, is there a better adjacent solution? With my performance with 06 was 30, but I got 2 more adjacent CPFs. One is 26, 2,6, and the other one it's 00. Okay, so I do my performance measure for 26 and gives me 36, and for 00 gives me 0. Is there a better performance against 06? Yes, definitely there's a better performance. So we go to our new iteration. In iteration number 2, step 1, remember we choose the edge that enhances z. Okay, at this point we have 3x1 give us a 3 unit advance, and 5x2 we cannot go through this way because if we continue we're gonna leave our Fresnel region, so there's no option, we got to move through x1. Okay, then step number 2, we stop at the restriction and the next restriction boundary. The next restriction boundary is given by 2,6. Step number 3, we solve the performance measure for the intersection of the new boundaries. So we calculate here how much is going to be the performance, and it gives us 36. At this point, we do again the optimality test where we ask if there's a better adjacent CPF. So at this point, my CPF, my performance measure with the 2,6 CPS is of 36. Adjacent CPFs are 0,6, that gives me 30, and also 4,3, that gives me a performance measure of 27. So here at this point, if you see, we don't have a better solution. So we can say that we have finished, and this is going to be our optimal solution. The geometric algorithm has 6 key solution concepts. The first key solution concept is that simplex method focuses solely on CPF solutions. We're working only with the corners. The second key is the simplex method. It's an iterative algorithm. We have been repeating steps. The third key solution is that whenever possible, the initialization chooses 00, the origin, as the initial CPF solution. Key solution number 4 says, given a CPF solution, it is much quicker to gather information about the adjacent solutions than about any other CPF solution. Key solution number 5, after identifying the current CPF solution, simplex method examines each of the adjacent edges. And number 6, a positive rate of improvement in the performance measure implies that the adjacent CPF solution is better than the current CPF solution, whereas a negative rate of improvement in the performance measure implies that the adjacent CPF solution is worst. At this point, with the geometrical algorithm, we are at we're at the beginning of stage number 3 of developing a computer procedure. Here we apply a geometric algorithm to the mathematical model. Finally, just to mention that most of the information in this video comes from the book Introduction to Operation Research from Frederick Hilliers and Gerald Lieberman. Thank you.